So first of all, let's see how autoscaling configuration actually works in EKS cluster. First of all, in the details section of our node group configuration, if we scroll a little bit down, here you see autoscaling group name. So an autoscaling group was created in AWS. And if we click inside, we are in the EC2 service, and this is the autoscaling group component. And what autoscaling group component in AWS does is basically groups or logically groups a number of EC2 instances together and has the configuration of minimum number of EC2 instances to scale down to and a maximum to scale up to. However, the autoscaling group is there just to group these instances. It doesn't actually autoscale our resources for us. So EKS does not automatically do this for us. We need to actually configure Kubernetes component that is running inside Kubernetes cluster that will use this AWS autoscaling group, and Kubernetes component autoscaler will together be able to scale up or scale down the EC2 instances for us automatically. Now let's see some specific examples of when this should happen and how this is going to work. So for example, if we have 10 EC2 instances in our cluster, and the cluster autoscaler, which is running inside the Kubernetes cluster, sees that most of these EC2 instances are underutilized, it will take the pods maybe from 2 EC2 instances and distribute them on the rest of them and stop those 2 EC2 instances. And this will obviously save your infrastructure cost on AWS because now you have 2 instances less running because you don't need that much resources. Or if the opposite happens, like you have 5 EC2 instances and the resources run out. So the next pod that needs to be scheduled basically cannot be scheduled on any of those instances because none of them has enough resources to start the pod. In that case, the autoscaler will take the configuration from autoscaling group, the maximum size, and start new EC2 instance or instances to schedule the new pods. And the maximum size basically lets us control the maximum number of EC2 instances that the autoscaler can spin up automatically when new pods need more resources. So why do we need to set a figure for the maximum number of instances? If we set the maximum number to say 20 instances, and we suddenly have a large spike in requests to our application, and more resources are suddenly required, even if our application could use more than 20 instances, the autoscaler won't be allowed to create more because the maximum capacity is capped at 20. One of the main reasons to set a maximum figure to limit that number is to save costs. Maybe we don't want to pay for more than 20 servers. As we know, the application can still handle a large spike in requests with this amount of servers. Or it could also indicate some security issue or some performance issue. Maybe we have a leak in the application that is suddenly using up so much resources. So instead of just spinning up more instances, we cap it at 20 and then we check manually why is our application suddenly requiring so much resources, and we can optionally then manually increase that number. But as I said, it can indicate some kind of issue with the application. And if we have a maximum limit of 20 instances, we may also want to have a lower limit and set a minimum capacity of 4 instances, for example, which will ensure that we always keep at least 4 instances running at all times. So even if our system could run only on 2 instances without any issues, one of the benefits to setting, let's say 4 as a minimum number instead of 2 is so that the application can avoid any latency issues that might happen if we suddenly get a higher load and need more servers, because spinning up new servers can take some time. This is the reason why it makes sense to define maximum and minimum number of instances in autoscaler configuration. Now there are a couple of things we need to do in order to configure autoscaler. First thing is the autoscaling group, which we already have. that automatically got created by the node group and has the configuration that we have defined. We can change this configuration at any time, desired maximum, minimum. The next thing we need to do is create a role for our node group or for our EC2 instances. So basically for the autoscaling to work, we need to give the EC2 instances inside the worker node certain permissions to make AWS API calls. And for that, it needs certain permissions. So we're going to go ahead and create a policy, a custom policy, not the one that Amazon provides out of the box. So in policies, we have the Amazon or AWS managed policies, but we're going to create a custom one that has a list of all the permissions that we need to give node group IAM role for the autoscaling to work. And I have the contents of the policy, and we're going to create a new policy. And we're going to create it from JSON document, and this is the JSON document with all the permissions. So basically, these are a list of permissions that this policy will contain. For autoscaling component, we're going to review the policy. Let's actually give it a name. Node group autoscale policy. And this is a result of the JSON file. Basically, this is the summary of our policy permissions. So we have EC2 instance permission and EC2 autoscaling component permission. And we're going to create a policy from this. And we're going to attach that policy to our existing node group IAM role. So if you go back to our roles, the node group role here has already 3 policies attached to it. So we're going to attach this newly created policy. So let's actually look for our policy. And it is right here. Node group autoscale policy. Let's attach it. And now our node group role has 3 managed AWS managed policies and 1 custom policy for autoscale permission. The second thing that needs to be configured is tags on the autoscaling group. So if I go back to the one autoscaling group we have for the node group, and if I scroll all the way down to the tags, this is key value pairs defined for autoscaling group component. And here we have a bunch of tags. And tags are also used in order for different services or components to read and detect some information from each other. And this is one of the cases where we have tags that autoscaler that we're going to deploy inside Kubernetes will require to auto-discover autoscaling groups in the AWS account. So again, the cluster autoscaler component, which we are going to deploy inside Kubernetes cluster, needs to communicate with autoscaling group because all the configuration is defined here. And for this communication to happen, the cluster autoscaler first needs to detect the autoscaling group from AWS. And it happens using these 2 tags here. We have the kubernetes.io cluster autoscaler EKS cluster test, which is EKS cluster name. And then we have cluster autoscaler enabled. So these 2 tags are for Kubernetes cluster autoscaler. And these have been configured automatically, so we don't have to do that or change that. So that's already existing here. And now, as a final step, we just need to deploy the cluster autoscaler component, which is a deployment component in our cluster. So let's go back to command line and execute following kubectl apply command. So kubectl apply -f, and this is the file that defines the cluster autoscaler deployment configuration. So we're creating that. And before we execute it, we can actually see the configuration So this defines a bunch of components here. Kubernetes service account, which is basically the user, cluster role, etc. Let's actually skip all the way to deployment. And this is the cluster autoscaler container itself. It's a deployment component with one replica, and it is gonna run in kube system. And all the way down here in the command part, we see the configuration where node group auto discovery is configured using these tags here. So we have Kubernetes IO, cluster autoscaler enabled, and this is the cluster name, which is going to be substituted by the real cluster name. And both of these tags are configured right here as we saw previously. So that's the configuration. And let's just apply the file so that all the components get created. So now we can actually check our deployment by doing kubectl get deployment in namespace of kube system called cluster autoscaler. And there you go. The cluster autoscaler deployment has been created. And now we're going to need to do a couple of changes to that deployment. So I'm going to do edit here. So we can edit the running deployment, so to say. First of all, we need to add an annotation right here in the annotations section. And this is the annotation. So basically it says cluster autoscaler.kubernetes.io save to evict is false. So that's the first change. And the second one is what we saw previously, which is the cluster name, right? Obviously, this is just a placeholder here. So we're going to change it to the actual cluster name. And our cluster is called EKS cluster test. And we also need to add some options in the command. These are balance similar node groups and skip nodes with system pods. And there is one final thing that we need to change here, and this is the image version here. So basically, this version needs to match the Kubernetes version that we are running in our cluster. And if we go back to our cluster information, we can see that AWS tells us the Kubernetes version information right here. So this autoscaler image needs to match that version as well. And the autoscaler image tag that matches this version or starts with this version can be found in Kubernetes GitHub repository right here. So that's going to be the new image name. So these are going to be the changes for our deployment. And I'm going to save this. And as you see, the deployment configuration got updated and the pod should be restarted, and we can actually now access the logs of the cluster autoscaler pod. Now, of course, as alternative to what I just did, we could also first download this YAML file, make all the changes, and then apply the edited YAML file, and then store that file locally so we know what configuration we actually executed. So that will be an alternative to applying the deployment and then editing it. But the results are going to be the same. So now let's get the pod of autoscaler application. And for each node, we basically have these processes. We have the kube proxy, which is a worker process running on each of the available worker nodes, which we currently have on all our nodes. Then we also have the core DNS, which always has 2 replicas running. It doesn't matter how many nodes are actually deployed in the cluster. And then we have the AWS node processes running on all of our worker nodes. So if we add another node, these AWS and kubeproxy pods will get scheduled on the new instance as well. And you also see we have autoscaler pod that is running on one of our EC2 instances. And we can actually see which instance that is specifically. if we do output white here. So I'm gonna do get pod, a specific one, and we're gonna have a detailed output with this flag. And in the output, we see the node name where this particular pod is running on. So now let's actually see its logs. Namespace cube system. And there you go. Maybe to make the logs a little bit easier to read, we can save it into Autoscaler logs file and see it in Visual Studio Code. So let's scroll all the way down. And here are some of the latest logs of Autoscaler where a couple of times the scale down process started. So it regularly checks all this information to decide whether the node group needs to be scaled down. So calculating unneeded nodes, and after starting scale down, you see the output no candidates for scale down. To see that now in action, let's actually set the min size of EC2 instances to 1, and then let's see what happens. So I'm going to go to the node group here. So I'll click edit. And let's put minimum size to 1 node and then desired to 1 here as well. So minimum and desired is 1, maximum is 3. Let's save these changes. And once the node group configuration gets updated and the autoscaler runs again to re-evaluate the status, we should see that node group will be scaled down to just 1 instance. So now that the autoscaler has run again with our new configuration, it has scaled down to just 1 instance. So let's check the logs here to see what happened. So first of all, we see both nodes, both instances with these IP addresses got marked as unneeded and ready for removal. So basically we changed the autoscale group configuration so the minimum number of instances is set to 1. And after that configuration change, the autoscaler started the scale down process. So here you see the autoscaler will check out the nodes in the autoscaling group. And as part of the scale down process, it will actually analyze when the instances were last used. We have 2 nodes that haven't been used for over 9 minutes, and then another one that has been used more recently. So after this evaluation, the preparation for removing these nodes will actually get started. And also we see the pod, which was actually our cluster autoscaling pod, is being moved to another node. So basically autoscaler decided, let's move this node right here, which just happens to be the first one of the 2. And the autoscaler itself was scheduled on this node, so it needed to move that pod and schedule it on another node. And that's what happened here. Also, as we saw at the beginning, each EC2 instance or worker node has its own default processes running there, right? These processes are there when the EC2 worker node initializes, and these are the Kubernetes processes. So core DNS pod was removed from the node here as well. That was originally scheduled there when we created that worker node. And towards the end of the logs, we see some other events happening. The pod is actually being deleted as part of the process, so we can see this cleanup message here. So the autoscaling service has now been moved and this pod doesn't exist anymore, as we see in the output. So the logs exited basically, and we have an error, which is pod not found. So after all this got executed, we can do kubectl get nodes now. And as you see, we have just 1 node running, the other ones were removed. Also, if we go back to autoscaling group and refresh it, we see instances is 1. We have the new desired capacity. We have the minimum and maximum. So desired capacity is something we configured at the beginning. However, using the autoscaler, basically this changes dynamically based on these values here and also the current EC2 worker node loads. So now if we started to deploy a bunch of pods in our cluster, and having just one EC2 instance here was not enough, especially because this is a T3 small instance, so it doesn't have that much resources, Autoscaler will actually run again and detect that we need more resources to schedule new pods and scale the node group up again. So obvious advantage here is that when you're not using the capacity of EC2 instances, it will get removed, so you save on the cost of that EC2 instance. However, the trade-off of that is that whenever we need a new EC2 instance because we ran out of resources to schedule the new pod, it will take some time because, first of all, the autoscaler needs to detect that we need a new EC2 instance in the cluster, and also starting and initializing that new EC2 instance will take some time. So a new pod scheduling in this case will not be that fast. So that's basically the trade-off between having this automatic intelligent autoscaling in the cluster and having to wait for new pods to get scheduled whenever you exceed your current worker node resource capacity. So that's how autoscaling can be configured, and that's how autoscaling works in EKS cluster. And we're gonna now start deploying some pods in our cluster, and we're gonna also see at some point that new EC2 instance will get created when we run out of the resources. So now that we have a Kubernetes cluster up and running with worker nodes, let's actually deploy an application pod and service into our cluster. So I have already created a very simple deployment and service configuration file for Nginx because we want to deploy an application that has UI so that we can also configure and see how accessing that application from the browser works when our cluster is running on AWS. So first of all, let's look at the deployment. It's pretty straightforward. This is a simple Nginx container, which is going to run on port 80, and that's it. That's our whole configuration. So this will start one Nginx pod in our cluster. And down here we have a service which is of type load balancer. And that is an important part here. So we're creating an external service in Kubernetes cluster that will have an AWS load balancer attached to it. Because every time we create a service of type load balancer, Kubernetes will actually create and spin up a cloud native load balancer depending on which platform we're on. In this case, it's AWS. If we were on Linode, for example, it would be a Linux load balancer so that we can access the application on the load balancer endpoint. And other than that, we just define ports here. This is the port of the service, port of the pod, which matches where the container application is running. And now we can execute this file to create deployment and service components. So let's do kubectl apply nginx config YAML, and let's execute it. Deployment and service got created. Let's actually check the deployment first, or the pod that it's running. There you go, Nginx pod is up and running, and now let's see the service. And there you go, this is our Nginx load balancer service. This is its internal cluster, internal IP address, and this is the external access URL. And as you see right here, it has ELB in the name, so this is actually the load balancer endpoint. So if I go back to AWS Management Console and go to EC2, because that's where the load balancer component is, here you see that a load balancer got automatically created. So this load balancer wasn't here when I created Nginx pod and service. This got created automatically when the service with load balancer type got created. the DNS name or the endpoint where this load balancer is accessible is this one right here. And this is exactly the same address or URL that we have here. And that's where now we can access our Nginx application. So if I paste this address in the browser, there you go, welcome to Nginx page. So we were able to access our application on this DNS name. Now, two interesting points to note here. The first one is right here you see the ports, right? You have the port of the service, and here you have the node port. So this is basically the port that opens on the EC2 node itself. However, because we're not using the IP address here, the external IP address of the worker nodes, for example, we can directly call this DNS name, and it will then, in the background, do the forwarding between those ports. So let's go back to the load balancer again. And right here in the port configuration, you see port 80 forwarding to 32,088. And that's exactly our port here. And port 80 is basically the default HTTP port. So whenever we do not specify any port, it's automatically defaulted to port 80. And this is the port where the load balancer is accessible at, and then it does the internal forwarding to the node port. And not to confuse this port 80 with this one, this is basically the service, the Nginx service port. So once the request gets redirected on this node port, this is a port that gets opened on the node, this request then gets forwarded to the service, which we defined to be accessible at port 80. So this is how the port mapping basically works. First from the request, from browser request to load balancer, from the load balancer to node port to service, and then to the final container application. So that's one point. Another point is that at the beginning, when we're creating a VPC for our worker nodes, we have defined two public and two private subnets. And as I mentioned back then, the load balancers, which are meant to be accessible from external requests, like browser requests, for example, are going to be scheduled in public subnets, because public subnets are the ones that are allowing internet traffic. Here you see availability zones where you can access this load balancer. And as you saw previously, when we created the VPC for our worker nodes, we defined two public and two private subnets in that VPC. And we said that the private subnets are the ones that do not allow external traffic in, and the public subnets will be the ones where the load balancer component will be launched into. So the IP address that the load balancer gets, the external IP address, will be assigned from the public subnet, and that's where the load balancer will be created. So if I go to VPC, and this is the VPC we created, and these are the subnets, the four subnets, two private and two public. And if I click inside each one, we can actually see in which AZ the subnets got created. So we have one public subnet in one availability zone in this region, and we have one private subnet in the same zone in that region as well. And in the same way, we have a public subnet in another AZ, and then once again, we have a private subnet in the same zone. So we're spanning basically two availability zones in our region. We have 3 in total, but we're just using 2 of them, and we have 2 subnets, one private, one public in each of these availability zones. So the pods are starting in a private subnet, and they also get the IP addresses of the private subnet IP address range, and the load balancers or components that need to be accessible externally are going to be created in the public, in one of the public subnets, and will get IP address from one of these subnet ranges. Important to note that these external components like load balancer, they will get both public and private IP addresses. So the private will be for the VPC internal communication, and the public IP address will obviously be for external access. And another thing is that in the load balancer configuration, you can also see the EC2 instances that this load balances the traffic to. So in the instances tab here, we're going to see all the EC2 instances, in our case, worker nodes, that are behind this load balancer. Right now, we just have one in one of the AZs, and this is the one getting all the traffic. And in AWS, there is a requirement for load balancers to have at least one EC2 instance in at least 2 different availability zones. So right now we just have one, as you saw before, in one of the AZs, and our load balancer is actually available in these 2 availability zones. However, there is no instance running there yet, so it's marked as unhealthy. So just a note for load balancers, however, in a Kubernetes cluster, we're usually going to run more than one worker node, so this shouldn't be a problem there. Now let's actually see an example of automatic autoscaling of our EC2 worker nodes when we increase the load on the only existing worker node. So I'm going to go back to the terminal, and I'm going to increase the replica size of my Nginx pods. So I'm going to edit the Nginx deployment configuration, and we called the deployment Nginx. And I'm just going to increase the replica count here. Let's actually set it to 20. And to kubectl get pod. So already you see some of them are running and the rest are pending. One of the reasons for pending state is usually that the resources aren't enough. So that means additional EC2 instance must be configured by the autoscaler to schedule all those pods. So let's also see the autoscaler logs right now. kubectl logs. And let's see what it's doing. And right here we see in the autoscaling logs that the group has scaled up. And we also see that some of the Nginx pods have triggered a scale up as well. And now if I do kubectl get nodes, we have 3 EC2 instances running again. And 2 of them have just started 4 minutes ago. And kubectl get pods. We see that all the pods got scheduled on these 3 different EC2 instances. So it worked pretty fast. If we go back to load balancer again and check the instances, now we see we have 3 instances in 2 different availability zones.